Thank you very much for the kind introduction, and thanks to Wolfgang and his team for organizing this, and to our friends from Princeton to coming over the pond for a rather short conference. So I have a deal with Wolfgang to do this in 5 minutes. So, as a result, I prepared 2 summary slides, and then it's up to Wolfgang whether we continue from there or not. So I'm going to stick to that deal. It's a joint work with Santiago Moreno, who is a PhD student of mine at UBC, and it is very, very preliminary at this point, maybe a bit too preliminary to be presented, but anyway, so all comments and feedback is very welcome. So, in a way it's good timing, because what I'm going to present, it is a very simple model. It fits rather naturally into what Patrick Chiaradito just presented. So the story here is a little different though. We can view this paper as a paper on securitization. Now, what is securitization? Securitization essentially has to do with transferring non-tradable risk into tradable financial assets. So a typical example are weather derivatives. There's an underlying risk, like temperature patterns, precipitation patterns, which is not tradable. Then you write security on this non-tradable underlyings, and then this becomes all of a sudden a tradable financial asset. So one of the ideas of securitization is to transfer this kind of risk to financial markets. Think of an insurance company. They are sitting on a portfolio of non-tradable or non-hedgeable risk factors, and then they write their derivative securities on these risk factors and sell it to the financial market. So that way they're going to get rid of some of their insurance-related problems. And so what are problems in the framework of the securitization? Number one, we have to design the derivatives our insurance company, or principal as we're going to call it here, is going to sell, subject to, of course, the preferences of the customers. And the point here is that the customers are heterogeneous, and the types, as we call it, their characteristics are hidden to the principal. So that puts us within an adverse selection framework. And typically, what we come up with is a nonlinear pricing rule for the derivative securities because of this kind of adverse selection problem. So there is, of course, an array of approaches to pricing derivatives on non-tradable underlyings. The most popular, or one of the most popular or common, is utility indifference valuation. So the idea of utility indifference valuation is very briefly summarized on top of that slide. So there are 2 agents called A and B. They both evaluate their individual risk by means of some risk measure. So I'm grateful to Patrick that he introduced the notion of risk measures. And the idea is that agent A sits on an initial endowment psi A and then designs a derivative called S and F and sells that derivative to agent B at a price pi, and such that the agent B is just indifferent between buying that security at pi and not doing anything at all. So in a way, what we get there is some kind of optimal contingent claim from the agent A's point of view, along with something which is sometimes called a price. I would prefer to call it a benchmark value, because this is very rarely a transaction price. Usually utility indifference is a valuation principle, not necessarily a pricing principle. Nobody typically ready to pay an indifference price. So it gives us a benchmark where to start, but it doesn't typically not give us a transaction value, unless, of course, all animals are equal, which means that this agent B actually stands for a large set of homogeneous agents. In that case, you can support this indifference value as an equilibrium price. And what we're going to do in this paper, we want to move away from this assumption of agent homogeneity, and we'd like to introduce the heterogeneous agent with private information, and this private information is hidden to the principal. And what we're going to show is that under some assumptions, this problem has a solution. So this was my 5-minute summary, and we can go from here or we can go to lunch. It's up to Wolfgang. So maybe 5 more minutes. So this is then the overview. So we have a very, very simple model. with a single principal. The single principal is our insurance company sitting on some risk which they cannot hedge through investments in the financial markets alone. There's a large set of small agents, but they're heterogeneous with mean variance preferences. So, I mean, that's a major limitation. We can do a little more general than mean variance. However, as we're going to go along, you will see where this assumption on mean variance actually plays a key role. The agents are characterized by their types, which in this case is just their coefficient of risk aversion, and that type is private information. So it's not revealed to the principal. The principal knows the overall distribution of risk aversion parameters, but not the specific realizations associated with an agent. So what the principal does, the principal offers what we call a catalog of derivative securities and prices, and the idea is to sell a certain asset called x of theta at a price pi of theta to the agent of type theta. Now, of course, in order to do so, this catalog that he offers has to be incentive compatible for the agent, so the agents really have to buy what is meant for them. Number one. Number two, it has to be individually rational, so if they enter these transactions, the agent, they must end up with a utility which is at least as good as some benchmark reservation utility, which is 0 in this case. Our work is very much inspired by a recent paper by Guillaume Caillet, Ivar Ekeland, and Lisa Tusi, which looked at this problem of derivative design within a principal-agent framework, but they looked at a model where the principal's goal is just to maximize revenues. So in a way, the principal has a linear pricing scheme. We look at a situation where the principal's goal is to minimize risk by selling derivative securities, and that makes this a nonlinear optimization problem for the principal. And we're going to conclude with some numerical simulations. I have two plots. I cannot compete with the movies we've seen, and one of the reasons is that it is a computationally extremely hard problem. So I'm unaware of any efficient numerical algorithm within the adverse selection / mechanism design literature that can deal with this kind of problem. So that's, from a purely mathematical point of view, another challenge and topic for further research. So here's the setting. There's a single principal, as I said, exposed to some risk. So this principal has a random endowment called W. Can be in L2, can be in L infinity. We don't really care at this point. This principal uses a coherent law-invariant risk measure on L2. So our agent had mean variance preferences. This is why risk measures on L2. With as the Fatou property, which is essentially some form of continuity, which is very important for our analysis later. And the goal of the principal is to transfer some of the risk, some of this W, by selling derivative contracts on W to agents whose type we call theta, and they're going to sell this x of theta to agent theta at a certain price. And the agent's preferences, as I said, are of mean variance type. We can do, as I said, a little more general. In this paper by Caillet et al., they look at mean variance preferences of mean variance type, so you can give them an initial endowment and then just characterize them by the proportion of money invested in different assets and call that their type. So our setting carries over to that. But just for the purpose of this talk, let's assume that agents have mean variance preferences, so expected value minus risk aversion times the variance. And this type theta, the risk aversion, is private information hidden to the principal. The principal, though, knows the overall distribution of types.
My understanding is that you quote the price for agents of type I, and then agents of type I could queue up and say, I want now.
Yes, but they could say, I want the product for agent J. But they could say that I want the product for agent J. So I'm going to design a derivative which is meant to you at a price. And I do the same with Wolfgang. But since I don't know who you are, you could come, if it's more beneficial to you, and buy the product which is meant for Wolfgang. So
Then I don't understand why the agent is not offering just one price.
Well, because they do it in such a way that you eventually reveal your type. So this is one of the restrictions that we're going to impose on the catalog. This has to be incentive compatible. So you, Dirk Becherer, buy exactly the product which I, as the principal, have designed for you. That's a condition that we impose later on this catalog.
Okay, so basically
Yes.
And your intention is that I buy the product that you want to be
Exactly.
type, but in principle this is just a list of products and Wolfgang and I could buy
Yes.
any of those, and it's just about gaining information.
But I designed them, this product, in such a way that that you buy what I want you to buy.
Okay. And the second question is, could I buy any amount of these things that we quoted?
No,
So
you-
that I want to buy none, 1 or 10, or is
No.
this price dependent on quantity?
It's a price for one product, so we're not going to allow this to be scaled. That would be a different product. So 1 pound of apples would be one product, 2 pounds of apples would be a different product. Why I need a FATU property?
It's redundant.
It is redundant, yes. Yes. Law invariant is fine, yeah. That's right.
On L2 everything is okay.
Yeah. Okay. So this is what our principle does. It offers contracts at given prices, and the agents can just choose. So they want to maximize their net utility subject to these available contracts. So we are just going to collect all these contracts in a set script X. Comes from L2, but L2 in the product space, okay, types times underlying probability space. And now comes what we call a catalog. So a catalog is essentially a list of products available to the agents along with their prices. And the agent can just choose anything from this catalog. They don't a priori have to choose what I want them to choose. So that's an extra condition, which is usually called incentive compatibility. So I, as the principal, have to design this contract in such a way that I really know what agent is buying what product, because that way I can calculate my risk, that way I can calculate my revenues. So that's one restriction, incentive compatibility, which forces the agents to reveal their types. And it has to be rational for the agent because they have an outside option. They can just choose not to enter the trade, in which case the revenue is 0 or the utility. So my catalog also has to be individually rational in the sense that it offers each agent at least her reservation price or utility. And then my goal as the principal is to minimize my risk by selling or offering these catalogs subject to this individual rational and incentive compatibility condition. So here is the optimization problem. I have my risk measure, I have my initial endowment W. I'm going to sell my securities, so I'm now exposed to an additional risk, which is this integral x of theta mu d theta. So if this catalog is incentive compatible, I know agent of type theta buys what I want him to buy. So this integral term is the additional risk I'm exposed to because I'm selling this product. And on the right-hand side, we have the revenues. The principal knows mu, but not the thetas. Sorry? Yes, but now if we take that out, that number we have a minus. So we reduce the risk by the revenues. That's for the principal. Yes, which reduces your risk. This is why there's a minus sign. So that's the principal's problem. Down there, then we have what the contract has to do for the agents. It has to satisfy their optimization problem. So they can choose any random variable x from the set of available contracts, utility minus what they pay for it. And I want them to choose what I want them to choose. So therefore, this catalog has to satisfy their optimization problem. So we get this value function v. And as I said, we make this assumption that they had an outside offer, so they can choose not to do anything, in which case they have a zero net utility, and therefore this function v has to be greater or equal than 0. So the whole point is now to rewrite the principal's optimization problem. In the form presented right now, it's probably not possible to solve it, so the goal is now to rewrite the problem in terms of a set of convex functions. And that is based on the notion of U-convexity. So what is U-convexity? U-convexity is essentially a generalization of convexity. So a function f is called convex, or with respect to another function u hat, if it can be represented in this way, where for regular convexity we would just have the inner product there. So U-convexity extends this notion of convexity, and this f can be written as the soup over some set utility minus what later becomes the price. So this is where the link is. We have a utility function of exactly this type, utility minus price. This is the agent's optimal utility, so this is where the link to U-convexity actually comes in, and we have the usual things, U conjugate, U subdifferentials, etc., as a normal convex analysis. So why is it essential to have U-convexity? Because there is a very fundamental result by, I think it goes back to Rocher, and then Guillaume Caillé took it up in his thesis, which essentially claims that if a catalog that the principal offers is individually rational and incentive compatible, it gives rise to a U-convex function. And vice versa, any U-convex function gives rise to such a contract. The result is summarized in that lemma, which again is due to Rocher and Cornet, as far as I know. So if we have an incentive compatible catalog, then this value function v, which describes the agent's optimal utility, is proper U-convex, and the optimal claim is in the U subdifferential of v, which essentially means the variance in our framework of the optimal contract is given by the derivative of v. So v is convex, almost surely differentiable, so that equation makes sense. And conversely, you give me any U-convex function, I'm going to give you an incentive compatible catalog in the following sense. The v stands for the optimal net utility. So I know the net utility, the utility after paying the transaction price. I know the U subdifferential. I take any claim from this U subdifferential. So then I know your utility, if I have that. I know the net utility, so as a result I know the price. So there is an equivalence between U-convex functions and incentive compatible and individually rational contracts. Now, if the principal's goal is to maximize revenues, that's essentially enough. That's all you need. You can go from there. In our case, we need a slight modification of this, and we're going to characterize incentive compatible catalogs in terms of convex functions. So what does it mean? It says that if a catalog is incentive compatible, the function v is proper, convex, non-increasing with this variance constraint. So it's very closely related to U-convexity. It's not quite the same. We move from U-convexity to convexity, but we have to throw in non-increasing, but the variance constraints remains the same. Vice versa, if we have a convex, non-increasing, non-negative function, then we have an incentive compatible catalog, very much defined in the same way as in the case of U-convexity. So this allows us to rephrase the principal's problem in terms of functions. And functions are much nicer to deal with than random variables or catalogs. So instead of working with incentive compatible catalogs, we are now working with functions which have nice properties, being convex, as a result differentiable, non-increasing, so relatively easy to handle. So what the principal can do now, the principal can first choose a convex function. Doing so, he specifies the agent's net utility. He can then design contracts by this variance constraint up here, this one, where we can normalize the expected value to 0, so that's just a transfer of money. That gives our principal a certain risk associated with a given function, and in the second step, then he chooses the function that minimizes the overall risk. So we can break this problem into a two-step problem. First, choose a function, minimize the risk for a given function. The function essentially tells us the revenue. So give me the revenue and minimize the risk for the given revenue, and then in the second step, actually optimize in terms of risk minimization. So this is the second form in which we can bring the principles optimization problem. So minimize the risk associated with your initial endowment minus what you sell to the agent. And then what we have here, this integral term, this is just, okay, this is not going to work. This is just the revenue rewritten in terms of this convex function v. And then we choose a function so as to achieve the minimum of this risk. So we optimize over this set C, set of convex functions, non-negative, non-increasing, convex with the variance constraint. As I said, we can just normalize expected values of the contracts to 0, otherwise we just transfer money back and forth. That's not a problem because of this translation invariance properties. And by and large, what this tells us is we can again rewrite the problem in form of some kind of variational problem, because what the revenues essentially depend on the function v, so the integral term there, but the risk only depends on the derivative. So in the risk part, only the x enters, and the x is linked to the v via the variance constraint. Variance of x is the derivative of v. So this is the form in which we can bring the principles problem, and we can solve that in two steps. Before we do that, some preliminary result. Suppose the principle has no initial risk, no initial exposure, and in addition to being law invariant, etc., our risk measure is also comonotonic, then it's optimal for the principle to do nothing. So that's relatively easy to show. In the general case, we have some upper bound on the risk and a lower bound, which we derive from our phi2 property, and from which we deduce that the v is bounded, so that's more a technicality. So let's get a bit more into the details. How are we going to solve the principles problem? So again, we have the variance constraint, and the variance constraint is the hard part. That's the nasty thing. Why is it nasty? Well, suppose that we relax that variance constraint to an inequality, and we look at all the contracts that satisfy this variance inequality. That is a convex set. It has nice properties, L2 bounded, etc. So now we have a convex functional on a convex set. That we can very easily minimize. Unfortunately, a priori there's no reason that the contract that we're going to derive from this optimization by looking at the restricted problem is incentive compatible. So we have to find a way to take this solution and to transform it into something which is actually incentive compatible. This is what we're going to do. So first step, we relax the variance constraint and we make it an inequality. Here, we look for a given function v at all the random variables that satisfy the inequality constraint on the variance. That set has very nice properties. And now we have a convex functional, our risk measure on a convex set, that has a solution. So the infimum here, if we restrict ourselves to this set xv, that has a solution. So if the variance constraint were not binding, the principles problem would have a solution. So now we have to find a way to take this solution, xv, and transform it into something which solves the original problem. And the idea is, to some extent, to take this contract and to push it variance-wise to the boundary. And the idea here is that the principle only looks at aggregate risk. The principle doesn't care about individual risks. So the principle has to find a way to redistribute risk within the set of agents in such a way that the aggregate risk remains unchanged and the variance constraints becomes binding for the agents. That's the idea. Now, of course, there's no way you can do this if you have only two agents. This is where the assumption of having a continuous set of agents actually is key. And also where, as we're going to see, this assumption of mean variance preferences comes in. So let me just illustrate in the first step this idea of pushing our contract to the boundary. So we take the solution that we're going to derive from the optimization problem where the variance constraint is not binding. And suppose now the agent would offer some form of hybrid product. So we take our derivative securities written on this, let's say, weather risk, and we throw in something which is independent of the weather, but which is, let's say, hedgeable. So then the agent, the principal, could choose to sell this benchmark claim here plus some variation, some type-dependent fraction of, let's say, an IBM stock. Assuming that weather and IBM is independent, we know what to do for this variance constraints to become binding, where we have to choose the alpha in such a way that this constraint there is satisfied, the equality. But of course we have two solutions, one positive, one negative. No, this is the key. Because we're going to, this function alpha turns out to be integrable, number one, and we have two solutions, alpha plus and alpha minus. So what we can just do, we can just define a threshold type such that the integral from 0 to that threshold type plus the integral from that threshold type to 1 sums is 0. That corresponds economically to a redistribution of risk among agents in such a way that the overall risk in this model remains unaltered. So from the principal's point of view, that's a great thing. Take the solution from the relaxed problem, redistribute risk in such a way that the variance constraint becomes binding, and in such a way that actually there is no additional risk at the principal's end. This is what this equality here says. And then that contract, now the variance constraint is binding, now that contract is actually incentive compatible. So that's the idea with hybrid products. But we don't want to throw in another asset, so we can tell very much the same story without throwing in an additional orthogonal asset. So we just take anything that we have that belongs to this set XV, and we use this product to push our thing to the boundary. So again, we have a variance constraint, so we have two functions, alpha plus, alpha minus, that make this equality and equality up there. Alpha plus is positive if you look at the formula, alpha minus is negative, so we can do the same thing. Again, everything is nice, continuous, wonderful, so we can find a threshold type so that below the threshold type we choose alpha plus, and above that we choose alpha minus. The agents don't care because it gives them the same variance, but for the principal it means, again, taking something away from Wolfgang, giving it to Dirk. Wolfgang doesn't care, Dirk doesn't care, and I just redistribute the risk within in the economy, so that I, as the principal, am not taking any additional risk here. So therefore, starting from the solution to the problem with the weak inequality, where the variance constraint is not binding, I can find a contract which minimizes the principal's risk for the given function v. Loosely speaking, which minimizes the risk for the given revenue. So that is what the first theorem there summarizes. And in the second step, of course, we have to choose the function which minimizes the overall risk. But that's the easier part. So we take a minimizing sequence, associated with that is a sequence of optimal contracts, and we show that while this has a convergent subsequence in a suitable space, and then we use the Fatou property to argue that the limit point actually solves the principal's problem. So I don't want to go into the details there. Now, the problem is, so we have a solution. The problem is that it's purely theoretical, and it is also more or less impossible to compute this in full generality. Well, as I said, it's computationally hard to simulate this optimal solution. I think it's actually impossible. Unless you restrict the principal to a certain class of assets, there's no way that we can get our hands on the optimal solution. So what I'm going to do now, I'd like to present two very simple examples where the principal's choice is restricted to a certain class of assets. The first can be solved in closed form. The second can at least be simulated in a relatively efficient way. So the first example would be what we call T claims, sometimes treasury claims, where the principal sells type-dependent proportions of some benchmark claim. The second example will be where the principal sells put options on his income. So the second case we solve numerically. The first case can be done more or less in closed form. So let's assume that the principal's only choice is to sell how much of a given benchmark claim to an agent of type theta. So all these contracts here are type-dependent multiples of some underlying benchmark claim. That can essentially be reduced to a variational problem. Namely, a variational problem of this form. Here's the risk, here's my income. Here is what I share, here is the aggregate amount of what I share for a given function v. C is given there in closed form. The only thing that enters is the variance, the derivative of v. And then we can, in a first step, fix an income level and minimize the risk. And in the second step, once we have the solution to this problem, minimize the risk subject to an income level, we actually minimize the whole thing. That is a variational problem because we have this integral of v prime here, which is what we really want to minimize. And the thing is that we can just do it pointwise here. Okay? So because we have this multiplicative decomposition here, it's really enough to just minimize this term here, this c of v. And that we can do that without any reference to the specific risk measure, by the way. So the risk measure at this point plays no role. We can solve that in closed form. The resulting function that we get has like a 1 over theta form, loosely speaking. And in the second step, so that was for a given income level. In the second step, we minimize over the income levels. This is where the risk measure actually comes in. This is where the risk measure plays a role. But again, that problem has a solution. I mean, here it depends on a model, depends on a specification, what this A actually is. But in principle, that is solvable in closed form. What is not solvable in closed form is the second case, underwriting put options. So let us assume now that the principal sells type-dependent put options on his income. So to each agent theta, what he actually sells is strike minus his income, positive part. But the strike depends on whom the actual trading partner is. And I just like to illustrate the effects by means of a very, very simple numerical example. But even that example, if you run it on a server in Vancouver, so maybe it's Vancouver, but it takes 2 days. It's an incredibly complicated optimization problem. And all the methods that we found in the literature, it seems like they are just not tailored to capture this kind of situation. So very simple situation. We have 5 types, 10 states of the world. Each state of the world is equally likely. And the income of our principal is just negative the state. So it's really very, very simple. And the principal evaluates risk by average value at risk. Now, the initial risk in this model she's sitting on is 9.75. And after transferring some of the risk and collecting the revenues, it is reduced to 4.35. So just to illustrate the effect that this kind of risk transfer has on the overall position of our principal. So as I said, I have pictures, nothing fancy. I cannot compete with movies. So this is the strike as a function of types. So we have 5 types, and well, we see this decreasing function. So the most risk-averse agent gets the highest strike. The least risk-averse agent gets, at the lowest, the least risk-averse agent gets the highest strike. And the optimal function V also doesn't look very fancy. And again, even to get this little very trivial plots, you have to run, but maybe it's Vancouver, you have to run this the simulation for anywhere between 24 and 28 hours. It's incredibly inefficient.
Did you talk to numerical analysis guy why it takes so long?
No,
Didn't brute force.
I want to do this on Tuesday when we're going to present QPL at Matheon. So this is a question I have for them. I mean, they're pretty good at simulating things and at numerics. We are not an expert, so we just took two actually algorithms that we found in the literature, which are kind of tailored towards min-max problems, and we applied these two. So maybe we just didn't choose the right ones. But the first one that we choose took about 48 hours, and the second one we choose about 24. So we are making progress here. But it seems like we just haven't found the right algorithm yet. So if somebody can provide one, more than happy to try it out. Yeah, well, let's see. So, I mean, this efficient numerical algorithm, that's one thing on the agenda for future research. Can we find something more efficient so we can simulate more interesting examples than type-dependent put options? But that's for a numerical mathematician. So what have we seen? Well, we have looked at a very simple principal-agent problem where a single principal wants to get rid of some risk by dumping it on individual agents. We've seen that under some assumption, this problem has a solution. The proof is not very constructive, so this means that we probably have to do numerical simulation. For that, we need an efficient algorithm. We don't have that yet. What else is there to do? Well, one thing, of course, is we only have a single principal. So right now, we are looking at a model where we have multiple principals to bring in some strategic interaction between these principals or insurance companies. The other thing, which Pierre-André Chiappori pointed out to us, is that in principle, you also want to have private information at the principal's end. I mean, if an insurance company sells you a certain product, you should ask yourself why. What is it that they know that we don't know that make them selling or offering these kind of products? So typically they know much more about loss distributions than you do. So maybe there is a signal sent by the insurance company if they make certain offers. So that's another thing which is left for future research. And I think we deserve our lunch break. Thank you very much.